All right, good afternoon. How's everyone doing? You had your labs, first labs? No, not yet. When is it? Tomorrow. Or different sections, different time. Does Has any lab taken place? I thought it did. Oh, it's the introduction. Okay. All right. You have your lab kits? Okay. All right. Let's see. Okay, so continuing on from what we discussed last class, we were talking about power supplies, right? And so we spoke about how uh, power supplies can be run in any mode. Benchtop power supply is constant current mode, constant voltage mode, and the mode of operation determines whether we refer to it as a voltage source or a current source. And so this here shows the Regal power supply that's in most of the labs, whether it's EE or CPE labs or lab rooms, you would come across this model. The ones behind you on the lab benches, those are from Keysight. There are a couple of EE labs that have the Keysight instruments, but again, the principle of operation is exactly the same. There's no difference. All right. Um, it's very hard to see. Obviously, it's nearly impossible to see, but I think right there at the top on these power supplies, it tells you or shows you CV. So it's either CV or CC, constant voltage or constant current mode. And this right at the top. And so these models, they would be something slightly different, and they would also have some notation somewhere. All right. Now we talk about batteries, right? There are batteries. We have coin cells, button cells, AAA, double A, C cells, D cells. They're all batteries. These batteries have chemicals inside them. There's electrochemistry that takes place. There are electrochemical reactions that takes place inside the battery. We used to have nickel and cadmium electrochemical cells. Then we had nickel metal hydride, right? Uh, those are rechargeable batteries. The batteries that are made from some kind of alkaline material, those cannot be recharged. They are used and throw away. Nowadays, every devices have batteries built in, so they are made from lithium ion. Then there are lithium polymer. Now there's lithium ion and phosphate chemistry. All of these are based on certain electrochemical reactions. These reactions result in a difference in electric potential between its two terminals. And hence, we have electrical voltage at its output terminals. Okay. That electrochemical reaction does not require a switch. As soon as it is manufactured, it is operational. And hence, battery quality starts degrading immediately. Whether you use it or you don't use it, those chemical reactions are already occurring. Okay. Batteries start degrading as soon as they are manufactured. So by the time the device reaches the consumer's hands, battery capacity is already depleted. If it's designed well and it's expensive, then maybe the loss in capacity is probably 1 or 2%. Otherwise, it could be as low as like 95 or even 90%. Just depends. All right, so all batteries are examples of DC voltage sources. All batteries are DC voltage sources. DC for the reason that the value of the voltage at the terminals is not going to change. Once it's designed for 1.5 volts, it's going to stay at 1.5 volts, theoretically speaking. Okay, so your battery is supposed to supply its rated voltage. So they're all DC voltage sources. All right, let's get to exponential and logarithmic functions. Now, I'm going to use the example of a diode to explain how and why we would use these exponential and logarithmic functions. Anyone ever see a vacuum tube? Probably not. They were the first electronic devices way back in the 50s and earlier. There were actual computers that were built using vacuum tubes. They were the size of these rooms. One computer right now, which fits in the palm or in our pocket of our hands, is now the size of a room about 75, 80 years ago. Vacuum tubes were cylindrical devices, glass or transparent. Typical vacuum tubes were the size of a human thumb. It's not really huge. But have you ever seen a old school television before the LCD and the flat panels came out? Right? Old school. They are known as CRT televisions, cathode ray tube. That scan rasters and pictures from the back. What we see from the front end is the end of a vacuum tube. If you ever open it up, you open up the entire box behind it, you would see that the glass screen is actually like a whole device, and the entire thing is a vacuum tube. Okay, and there are images and videos floating around on the internet. If that interests you, you can simply do an internet search and look it up. So that entire thing was an actual tube. Okay, but let's come back to our device here. So this is a vacuum tube. This vacuum tube had an electrode that was known as the cathode. It had a second electrode at the other end that was known as the anode. You might be familiar with these terms, anode and cathode, from chemistry, perhaps. Right? So you have these two electrodes. Hence the name of this device. This device is known as a diode. Di stands for two electrodes. So this is a vacuum tube diode. Okay, vacuum tube diode. And of course, Di stands for two electrodes. So the way it would work is you have this filament. This filament would be heated up. The filament heats up. Cathode is in close proximity, so the cathode heats up. And the cathode heats up, the electrons that are released by the atoms of the cathode material, those electrons float kind of on the surface of the cathode, right? Now, I'm showing it's floating as if like there's a big, large distance, but it's not, right? It's not that large of a distance. It's like size of the atom. So subatomic particles, they're just free to move around. So they're just kind of like floating on top of the surface. What charges do electrons have? Negative, right? So what if you took an external power supply with plus and minus and connected in this way, in this manner? What do you think would happen? Anyone? Yeah, I see some signs for a loop. Your anode is now connected to a positive potential. Your cathode is connected to the negative. So if your anode is held to a higher potential, meaning positive charge, the electrons are attracted to that positive charge. And then electrons will start moving in this direction. So now there is electric current flowing through that circuit. Okay. The flow of electric current is taken as opposite of the flow of electrons. So current I is flowing in the opposite direction. If electrons are going from left to right, current flow is from right to left. So current is now flowing through that device. And that is the first or the most fundamental of electronic devices, the vacuum tube diode. Now, obviously, there was no way to control the flow of current in there. And so that came in later tubes. Yes. Yeah, that's an E. Just electron moving. And so technically it should be E minus, just to indicate the negative charge and electron. So electron. Okay. So as I said, there was no way to control the flow of these electrons once they are released, right? You just apply a voltage externally, and whatever electrons are there are going to continue to flow through there. So there's no way to control it. So then they added a third electrode in there. That third electrode would be along the sides of the tube. And because it's a third electrode, now you have a trio of electrodes. So now it's known as a triode. You had a fourth in there, now becomes 4 electrodes. So it becomes quadrode, pentode, hexode, and so on and so forth. I think beyond a certain number, they just gave up and started calling it 8 electrode vacuum tube or a 9 electrode tube. I personally have never seen anything more than a 4 or 5, and that was a long time ago. I've seen images on the internet where you have more than 10 electrodes, like up to like 15 or 16 of them. I've never studied those. I've just seen images. It's all in the pursuit of gaining actual control, right? So why are we talking about all this? Well, when the first semiconductor device was created, right, the nomenclature of the diode, the anode, and the cathode, everything was carried over. And so semiconductor diodes or semiconductor two-terminal device is still referred to as a diode. Not still, but that was the name it came. So it's always going to be a diode. Even though it does not have any electrode in there, it is still known as a diode, meaning two electrode device. The name anode and cathode also carried over. So the symbol of a diode is a triangle or an arrowhead, and there is a line at 90 degrees at the tip of that arrow. And the line indicates the cathode, and the other end is the anode. So even though they are not electrodes anymore, they are still referred to as the anode and cathode. All right, let's take a pause. Let me know if you have any questions. Are there any LEDs in your kit, in your lab kits? There are LEDs too? Just one? Okay, interesting. The acronyms or the symbol that is used for these terminals is A and K. Remember how I was talking about C? What is C used for? In physics, let's say. If capacitance, charge, coulombs, light, lots of other things. So cathode was indicated with a K. And it's still true for semiconductor diodes, right? Semiconductor diodes are still referred to as anode and cathode. Now, if you look at the lab kit and you have a regular diode, or any kind of diode for that matter, the most typical packaging for the 1N4000 series is a black opaque epoxy package. And there is a cylindrical band running around that package. It's either gray, it says grayish silver band. That band indicates that terminal is the cathode. There are some other specialized diodes, Zener diodes, and then there are some other different variations of the diode that come in a transparent glass-looking package. It's more like, it's like plastic epoxy, but it's transparent. And it has a black or a red band. And that band, again, indicates that the terminal is the cathode. Okay, so if you look at the actual device, you will see that. LEDs, you'll have two leads coming out the same side. The longer lead outside is the anode, the shorter lead is the cathode. All right, so where do the exponential functions come in? Well, you know how we talked about resistors, capacitors, inductors, they are linear devices. The relationship between the voltage and current is linear. As one quantity increases or decreases, the other quantity also increases or decreases. But not so for the semiconductor devices. The semiconductor devices like diodes and transistors, FETs, BJTs, they all have a non-linear relationship between the voltage and the current. And so here is this equation. This equation describes, this is known as the diode equation. It describes the relationship between the current and voltage of a diode. It's an approximation, and it's fairly accurate approximation for under most environmental conditions. Okay. So it basically states the diode current I is the exponent of the diode voltage V. So current for a diode is proportional to the exponent of the voltage. E raised to V. Okay. Hence, we will encounter these kind of functions throughout 115, 215, and E15, 315. And of course, this equation has a lot more. There are several other terms. We don't go through all of them. Again, this is something you will study in 315 in higher classes. VT is known as a thermal voltage. Thermal voltage is present in all semiconductor devices. Due to the thermal effects, there is a certain voltage that is created in these devices at room temperature. It's very, very small. It's 25.6 millivolts. Very small voltage, but it's an integral or an important part of the equation. All right. Periodic functions. So we talked about DC voltages, right? DC voltages have a constant value with respect to time. Now we talk about AC. AC voltages and currents in general. So you would often hear the term signal, waveform, function. They can all be used interchangeably. In that sense, they could be used as synonyms of each other, even though they don't mean the same thing. When it comes to electrical engineering, we use them as analogous to each other. So could be a signal, could be referred to as a function, could be referred to as a wave, or a waveform. Okay, signal, function, wave, or waveform. In fact, if you look at one of those devices at the lab benches, there should be something labeled as a function generator. That function generator, as the name suggests, generates a variety of functions. Those functions are signals like sine waves, triangular waves, square waves, ramp, sawtooth, noise, arbitrary random signals, etc. And a function generator is nothing but an AC power source. That's all it is. A signal generator or function generator is simply an AC power source or AC power supply. Okay, AC power supply. Okay. All right. So AC voltages and currents. And then why are they known as periodic functions? Well, they're known as periodic functions because they change their value at any point in time. Not change their value. The value of these functions, the value of these voltages, the value of these currents is different at any given point in time. If we make a plot or a graph of the value of these signals as a function of time, they follow a certain pattern. If the pattern looks like a square wave, we call it a square wave. If it looks like a rectangular wave, we call it a rectangular wave. If it looks like a sinusoidal waveform, we call it a sine wave. Sinusoidal is spelled like this. Sinusoidal. Mathematically represented by the functions sine and cosine. Okay, so sinusoidal functions are sine waves. Mathematically can be represented either with a sine or a cosine function. And the reason they're called periodic is because the value of these functions, let's say it starts from 0, it goes through a positive cycle, comes back down to 0, then it goes negative, and then comes back up to 0. And we say it has completed one full cycle. From that point on, it starts to repeat itself. And that's what makes it periodic. Okay. So if I was to plot this, if I was to plot, let's say, the AC power outlet, we have T on the x-axis, we have 0 on the left, and we have plus V and minus V. Our waveform will have certain value at all points in time, right? And so it's going to go it's going to go to a positive peak, come back to 0. It's going to go to a negative peak and come back to 0. From this point on, it's going to start repeating itself. Okay. So the point where it starts repeating itself is known as the time period of that waveform, or one time period of the waveform. It is indicated by the uppercase T. It is also known as one full cycle. Okay, one full cycle. All right, one full cycle. So again, time period of the waveform is the point where the waveform starts repeating itself. Let's take a pause and go over all of that. Let me know if you have any questions. So far, so good. Okay, so at this point, I will ask you, what do you think is the value of the voltage of our power outlets, at least here in North America? It's a general knowledge question. We don't have to be engineers to note that. Anyone? 120, that's a good guess. Anyone else? 240 is also a good guess. It's 120 in North America, 240 outside. Okay. So when they were first setting up the power stations, this is like early days of electricity generation. People had only seen electricity in in lightning storms, which would actually kill people. So it was very dangerous. So they settled on a nice round number of 100 volts, 10% tolerance. And so it's 110 volts, but it's anywhere between 110 to 120 volts. right? So North America is 120, outside it's 220, 230, 240, all right? Yes. So good question. The question being asked is, why is it different? The answer, it's a good question. I'll just get back to that in just get to it in a minute. So it's 120 volts. Anyone know what the frequency is? Yeah. Anyone? The answer is probably in your backpack. If you have laptop adapters or chargers, or pretty much anything that you plug into a power outlet, will always, always, always have a spec label on top of it. So if it's a small appliance, large appliance, laptop adapters, mobile chargers, everything has a spec label on it. Your laptop adapters, your mobile chargers actually have two ends. There is an input and there is an output. So both of it is listed. Okay. You plug your laptop adapters into a power outlet, so something is going in, right? So it'll tell you AC input voltage, and then there's DC output that's coming out. And so it'll also have DC output voltage. It's a small appliance, it'll tell you rated for 120 volts. You plug it into a power outlet. If it's a large appliance, also it will have a label on there, safety warning and safety label on there, which says either 120 volts or 240 volts. Okay. So if you look at your laptop adapters, probably slightly easier to read than your mobile phone chargers, which are very, very small, but it will be there. So previously, up until like a few years ago, at least until mobile chargers showed up, we'd have to, if you traveled from one country to another, we would have to perform a physical conversion of our adapters as well as an electrical conversion. Okay, meaning the prongs would look physically different. Here in North America, there's flat prongs. In other parts of the world, they are slightly thicker, or in most parts of the world, they are like cylindrical. Okay, and so that's a physical conversion that is required. Plus, you'd have to change the voltage from 110 volts to 220 volts. So electrical conversion will also be required. Not so much anymore. Nowadays, if you look at your laptop adapters, it will state AC in or AC input can be anywhere from 100 volts to 240 volts, 50 hertz to 60 hertz. So North America is 120 volts and 60 hertz. Other parts of the world is 220 volts, or let's say 240 volts and 50 hertz. Frequency does not matter as much, but the voltage does, and I'll explain why. And then your chargers have a DC out. So the DC out would be laptops more often than not run on 19 volts. It'll be like 19 volts, and then the power adapter, depending on how much current it can supply, it'd be like 4 amps, 5 amps, 6, 7, 8, 9, 10 amps. Okay. So my laptop is, I want to say, about 12, 13, nearly 15 years old. It has a brick of a power supply. It's about 250 watts or something. So it's 19 volts and about 10 amps of current, which is like ungodly amount. Okay, huge. So DC out, let's just say typical cell phone or tablet charger would be 5 volts. And then let's say keep it small. The first ones were actually only 1 amp, and then came along tablets. They were like 2 amps. So 10-watt charger, 5 times 2, 10 watts. A computer's USB port, by the way, USB ports are standard. A standard USB port is always 5 volts. That's a universal spec, whether it's on a desktop, on a laptop, whether it's a separate charger, doesn't matter what it is or what device it is. A standard spec USB voltage is 5 volts. A computer or a laptop, the spec is limited to 500 milliamps or 0.5 amps. So very low. So you could charge your phone in a laptop or a desktop, but depending on the power rating capability, it will charge very slowly. So when the first smartphones came out, it was 5 volts and 1 amp, so 5-watt chargers. Then came along tablets with bigger batteries. So they increased the charging speed by increasing the current. And that's where it leads me to the answer to your question. I'm getting around to it. So a 10-watt charger for a tablet would be 5 volts and 2 amps. But the USB spec was capped at 5 volts. So if you wanted to charge your devices faster, you got to supply more power to it, right? You want to charge it faster, you got to supply more power to it. If you want to supply more power, your voltage is constant. Electrical power, by the way, is the product of voltage and current. P is equal to V times I. So if you want to supply more power, you either increase the voltage or you increase the current. Now, tablets have a much larger battery than smartphones. So if you want to charge it at the same rate as a smartphone, you got to supply more power to it. So instead of 1 amp, you now supply 2 amps. Then came along fast chargers. Instead of 2 amps, you now supply 3 amps, 4 amps, 5 amps. So now you have 50-watt chargers. So you can supply 5 volts, 10 amps. Then came along USB-C, USB-C power delivery. So USB-C PD. USB-C PD not only allows increase in current, it also allows you increase in voltage. So depending on the device, that power supply can mix and match or cross supply increased voltage and increased current. My phone is from outside of America, and I purchased it a couple of years ago. And it has a 120-watt charger, 120 watts. It can go from 0 to 100 in like 20 minutes. I tested it out when I first came. I drained the battery all the way down to 0, plugged it in, 20 minutes, right on the dot. So 120 volts, it's increasing the voltage as well as it's increasing the current. Okay. The downside of that is the more power you're supplying, the hotter it gets because thermal energy, there's no way to escape it. Electronic devices generate heat. So when electrical energy is converted into a different form of energy, a lot of it is lost as heat. And so it can get hot. That's why they always say, don't use your phone or your devices while it's charging, because you're generating more heat. The charging itself, a natural byproduct of charging is heat. And then if you use the device at the same time, it generates even more heat. All right. Any questions so far? All right. So the answer to your question, the question asked earlier was, why is North America capped at 120 volts and why are other countries, at 220 or 230 volts? The answer is more power can be delivered. When they first started, the systems were all designed for 100 volts. After that, it's impossible to change it. I guess it's possible to change it, but it would cost you trillions and trillions of dollars to replace everything. All transformers, all wires, all circuits, everything just runs off 120 volts. So there's no way to now change it all out to like 240, right? And so that's the reason. So taking it one step further, power is V times I. In terms of resistance, and this is something, again, we'll study later on, is I square times R, resistance, okay? So when you're transmitting electrical power or long distances, it's going to lose some energy. Power is dissipated as heat, okay? Long distance transmission lines that you have seen running all across the country, right? So they are hundreds of miles long. And so when you're traveling hundreds of miles long, it has some resistance. A lot of power is dissipated as heat. There's energy losses that occur. So if you increase the current, the power loss increase as square of the current. So you want to keep the current low and you increase the voltage to transmit the same amount of power. Okay. As a real life example, you could have large appliances in residential areas. Let's say a hot tub. You ever hear about or see well, see or hear about, like you had to have an electrician come out because you wanted to get a hot tub installed. Anyone ever hear of that? So when you want to have a hot tub install, a hot tub requires huge amounts of power, which is not possible because it exceeds the residential power rating. Okay, because you have to heat up a large quantity of water, plus you have these jets and pumps and stuff. And so to increase the power, the electrician will come out, obtain license from the county or the local government, will run 2 lines, 120 volts in series with 120 volts. Now you have doubled the voltage that's coming in. Instead of 120, now it's 240. And so with the same amount of current, now you've increased or doubled the voltage. And so you can run high power appliances with that connection. All right, let's take a pause and let me know if you have any questions. Yes. It's dependent on the resistance also. It's dependent on, so the question being asked is, why is it I squared times R? It is also V square over R. So current has a more of an effect than voltage, because it mathematically V equals IR. When you combine these two equations together, you get this equation. P is equal to I squared times R, or V square over R. So voltage is divided by R, whereas current is actually multiplied. And so the losses or the power that occurs is more with current than less with voltage. You could increase the voltage, power losses will still occur. That's a very good question. So power losses will still occur even if you increase the voltage. But it is actually divided by the resistance, not multiplied. With the current, it's multiplied. In general terms, they are known as I square R losses, based simply of the mathematical expression. The mathematical expression is I squared times R, and these losses that occur in these systems are known as I square R losses. It's just used as one single word, I square R, I square R losses. Okay, coming back to our topic under discussion. So we had this time period of this waveform. It's 60 seconds. Now, what does it mean? Well, one full cycle, meaning it starts from 0, goes to a positive peak, comes to 0, goes to negative, comes back up to 0. That's one full cycle. It is also defined as the time period of our waveform. And the number of cycles in 1 second is defined as the frequency of the waveform. So the number of cycles in 1 second is defined as the frequency of that waveform. How frequent the waveform is. Okay. And the unit for frequency is named after the German Austrian physicist Heinrich Hertz. Nothing to do with the car rental company. And acronym for Hertz is HZ. HZ, Hertz. Okay. So the frequency is the number of cycles in 1 second. So power outlets in North America, we said it's 60 Hertz. That means in 1 second, the power outlet goes to a positive value, negative value, positive value, negative value, positive value, negative value. 60 times in 1 second. Okay. Does that seem fast? Yes, to our human perception, it is fast. But here's the thing though. In terms of electrical engineering, it is actually an extremely very, 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 very low frequency. Human hearing is technically defined as 20 Hertz to 20 kilohertz range. right? But my hearing, even from like when I was a teenager, I used to like wear headphones all the time. So at this age, nearly I realized I shouldn't have done that. I probably can't hear anything below 100 hertz. 60 hertz is a very low frequency. As an example, we are surrounded by wired and wireless signals all around us. AM broadcasting stations, they are broadcasting at a frequency of kilohertz. So 640 AM, the call sign represents the broadcasting frequency of that radio station. 640 AM stands for 640 kilohertz. That's the broadcasting frequency. FM radio stations, 101.7 FM. That 101.7 technically means it is broadcasting at a frequency of 101.7 megahertz. FM stations work at megahertz range. Your wireless routers, cordless phones used to be 2.4 gigahertz. Dual band routers, 5 gigahertz. Terrestrial broadcasting systems are again in gigahertz, megahertz range. 10⁶, 10⁹. Satellite communications, like in the terahertz range. The processors in your smartphones, in your laptops, are at least 2 gigahertz, if not more, or at least 1 gigahertz, if not more, right? That's very high operating frequency. So 60 hertz is considered to be very low, right? All right, so it's 120 volts, 60 hertz. That means it goes up, goes down, goes up, goes down, 60 hertz, 60 times in 1 second. Mathematically, we represent the function with as with sine or cosine functions. So we say A sine omega t. Omega is the angular frequency. F is the standard frequency in hertz, which is the inverse of time. F is equal to 1 over t. T is in seconds. Now, to concentrate on A. A represents the peak value of this waveform. So this value is A. Peak value. Now, if, let's draw it out here. This is A as measured from 0. It's half above and half below 0. What is the average value of this waveform? 0, right? So since it's half, obviously the drawing is not, not accurate, but that illustration is half above, half below 0. So if it's half above and half below 0, and the average value is 0, is there energy being transferred? Mathematically, we would say no, but realistically or physically, yes, it is being transferred, right? We plug something into the power outlet, it works. So energy is being transferred, energy, power is still being sent to our devices. So how can we mathematically represent this? Well, any function, whether it's voltage or current, is a function of time. So it's V of t or I of t. Voltage as a function of time. Time is the variable. It can take on any values. So t could be equal to 1 second, 2 seconds, 3 seconds, or 0.1 second, 0.2 microseconds. Could take any value. But voltage is a function of time. So early on, researchers decided, well, instead of trying to find the average value of this waveform, what we will do is we will first square the waveform. So we square the waveform. Actually, this is not the place to do this. Let's go here. So we have this waveform. This is A or peak. And then trying to find average value of VT. So first square the waveform, then we take the average. Okay. So to take the average, we integrate it over one single time period. So 0 to t. Integrating is simply summation. We simply divide up in individual slices. The individual slice is dt. And integrating simply means you are adding up all the slices within that one time period. Once you add everything up, now you take the average. So you have 1 over t, or divided by t, that is one time period. And because we squared the waveform at the beginning, now at the end, we do the opposite. And we take the square root. And hence, we come up with a new term to describe the value of this voltage or this quantity, which is known as RMS. Literally stated, RMS is root mean square. It comes from the fact that this value is the square root of the mean of the waveform. RMS. And RMS is a quantity in its own right, or not quantity, but a acronym or a actually, yeah, quantity works. Okay, so it's not quite the average value, but it describes something similar to that. Right, so RMS value is one single point. The way I like to describe it is, let's say you take all these positive, negative peaks, and you flip them all positive, right? If you flip them all positive, and so on and so forth, now they're all positive with respect to t. Let's say if these are mountains of dirt or hills of dirt, and you flatten them out to a plateau. Okay, you flatten it out to a plateau, and you fill in all the gaps. The value that you obtain would be the RMS value. And hence, RMS value is one number, whereas the peak value or the waveform as a function of time can have any value. Okay, RMS value is one single number. So we only have a few minutes left. But again, RMS values are only one single number. So the 120 volts is RMS. It's not peak. And 120 volts that we're talking about is one single number, and so it's RMS. Anything that you measure in the lab with a meter, with a benchtop meter, or even a handheld meter, is always RMS because it's providing you one single value. That's always RMS. Any meter measurement is always RMS. DC doesn't matter. DC is always constant, so there's no RMS value for a DC. Okay, there's no RMS value for a DC. DC value is just the DC value. But for AC, the RMS value is one single number. Technically defined, a RMS value is the value of the AC waveform that would produce the same power or the same energy in a resistor as a DC equivalent voltage or a DC equivalent current. So in that sense, we could say it's the DC equivalent of an AC waveform. So 120 volts is RMS, but the peak value is not RMS. The peak value is not 120. The peak value is actually 170, which is where this one comes from. Peak value is 170. And that is also only one peak, one positive peak. So this is plus 170, and this would be minus 170. So in 1 second, a power outlet goes from 0 to nearly 170 volts in the positive direction, and then again 170 volts in the negative direction. It technically is around 169 point some value, 169 volts. But let's just say 170. So there's a total swing of 340 volts. Okay, in everyday life, we simply use the RMS values, but it is very important to also be aware of the peak values, because 60 times in 1 second, it's going to exceed those peaks. So let's say you are designing a system. Let's say you have a capacitor or a device, and you'd think, okay, it's 120 volts, right? So let me just find a component that can handle up to 140 volts, right? You just design a system with 140 volts, you plug it in, what's going to happen? It's going to get blown out because 60 times in a second, it's going to go above 140 all the way to 170. So that's why peak value information is important. Peak values can be observed on oscilloscopes, right? Or special purpose devices, but it's easy to observe waveforms on oscilloscopes. Everywhere else, unless explicitly stated, they're always RMS values. If it's peak value, it'll be stated, right? Okay, so we'll end class here today and we'll pick up here again on Friday. Oh, my office hours are updated, and so I'm going to post them, but it's Monday and Wednesday from 11 to 12, and Thursday, which is tomorrow, from 3 to 4. And I'll have my website updated later tonight. Yes.